Let's talk about another application. Let's think you're driving along and your car hit, or riding along, and your car or vehicle hits a speed bump, and the vehicle goes bump and then kind of wiggles a little bit and settles down. Now ideally it's supposed to just wiggle once and settle down without oscillating over and over. That's what my mechanic tells me. But let's say your shocks aren't very good and it wiggles a lot before settling down. I didn't have the budget to buy a car to show this demonstration, but I did manage to afford an old bottle of water and some dominoes and a rubber band. So we're going to pretend that the rubber band is our spring. It's pulling instead of pushing, but that's good enough. So here I've loaded some weights in my water bottle, and the harder I pull the spring, the more it stretches. And you can see the water bottle will bounce up and down like that and eventually settle down. Another way to think of it, instead of the harder I pull the string, the more it stretches, the spring, the more it stretches, the harder, the farther I stretch the spring, the more it pulls. Here it's pulling enough to hold, I don't know what that is, 10 dominoes or something. And if I added more dominoes to it, it would sink down, and then it would be stretched harder, and it would be pulling up hard enough to hold that higher number of dominoes. So me and my kids took some data on this. I'll show you that video later, but I've summarized it into an Excel sheet, of course, so let's switch to that. All right, here's our data. We did 2 rounds because anything worth doing is worth doing repeatedly. Anything worth doing is worth doing repeatedly. So we had 2 rounds of data, counted the number of dominoes, had a tape measure going and everything. And so here's the data we collected. It's interesting that the 2 rounds of data shown in blue and orange here were kind of systematically different, even though I had pre-stretched the rubber band. So it's not like the more stretching the rubber band probably made a difference. I might have been reading it differently, I don't know. So I fit 2 trend lines here, but maybe it's better to think of it as just one data set. It's clearly not perfectly linear, but I think a straight line is nice and easy to deal with, so let's work with that. So here we're thinking of it as however many dominoes you put in the weight gives you a longer stretch. But I want to think of it the opposite way. The farther stretched it is, the more dominoes it can hold up, the more force it exerts in response. So let's take this idea and go formulate some stuff. So we're saying the force of the spring's pull is this constant, which we got from the trend line, times how far the spring is stretched. And we'll ignore friction to begin with. So we'll go like 20th of a second by 20th of a second. We'll start and say like it's 2 centimeters extra stretched and it's at rest. And what force is acting on it? Well, the spring is pulling it backward, so we got a negative times the force constant here times how far it's stretched, the length of the stretch in centimeters, and then that's a force and it acts on a mass, so the more the mass is, the less acceleration you get, dividing this way. I've got to figure out the whole dominoes versus newtons and kilograms and stuff, so I've got to mix up somewhere, but the math is all right, it's just the physics that's wrong. I'm sure that's comforting. So that's the acceleration we get, and then how do we go forward one time step? Well, the new velocity is the old velocity plus the acceleration times the change in time. That's just our calculus prediction equation. It's almost like a tangent line function. In fact, it basically is. And then the new position is the old position plus the velocity times the change in time. Again, that's our calculus prediction equation. You might have expected me to use the previous velocity, and you can, but it turns out it's better for really interesting and complicated reasons to use the new velocity instead of the old one. There's something called the leapfrog method and Euler's method and stuff. We can talk about that later if you're curious. So then we've got new position, new velocity, and from the new position I can compute the new acceleration, and then I use that to update the velocity, use that to update the position, and so forth. And what kind of graph do you think we get? I've got it snuck off to the side here. Does this make sense that the position, it was originally more stretched out than it needed to be, or than its rest length, and then kind of went less stretched and then more stretched. And how would you describe that? Probably a sine wave. And it turns out that in theory that is exactly a sine wave if I took infinitely small steps and had no friction and perfectly proportional pull based on the position. So that's a lot of fun without friction. With friction, now we've got the same acceleration, but then subtracted from that a little bit based on some friction constant and the current velocity. And the graph we get is this. It starts out like a sine wave, but the amplitude is getting smaller and smaller. So we could model this as a sine wave at some frequency. I'm using W because often we use omega, which looks like a W, times some kind of exponential decay. And so that kind of oscillating but settling down is a really important common theme in lots of math and physics. I want to show one other thing here. If I increase the mass, what do you think will happen to how long it takes? If I have a heavier object on the same kind of spring, let's bump the mass up to twice as much. It seems to take longer to oscillate. And that's actually related to how astronauts weigh themselves in the space station when there's no gravity to pull them down onto, no gravity that would pull them down onto a scale. Kind of fun. So that's another big motivating example, using acceleration that's a function of my current position and maybe even velocity to update my velocity and then update my position. All kinds of physics going on there, this interesting decaying sine wave stuff.